Hi everyone, and welcome to week 24 and 25 of the BinarX Student Payload Development Program entitled Breadboard Payload Prototype. So in these sessions, we're going to go through how to go from a problem statement to an analog sensor circuit. So Will Blackie, our engineering support, is going to run most of this and explain it. And then if you can, just go through it and see how it applies to your own payloads, that would be great. You'll be using the visible light photodiode and the little op amp that were recently delivered to your schools or your teachers. And make sure you've got all the parts on your lesson plan ready to go, and you can put together that circuit, calculate the resistor you'll need, and just follow along. So we're going to go through problem statements, measuring light, block diagrams, which you'll remember from last term and that you'll need to update from for your preliminary design review presentations in December at Curtin University. Amplifiers or operational amplifiers or op amps, which we touched on last term, schematics, and much more. So this session is a long one. You'll want to split it into multiple weeks this week and next week, or more if need be. And as always, if you're stuck, you can email us at binarx@curtin.edu.au. And this is a really useful couple of lessons for those of you who are doing different parts of the spectrum and trying to look at that with your sensors, because this will be applicable almost directly to your payloads, and it's just a good one, regardless of your payload, to have an understanding of, even because it's a tricky one. So we're just going to introduce it and walk you through it. And good luck. Thanks for listening.
To practice developing a payload, we're going to start with a problem statement. For your schools, these objectives are science related, and to not give too much away, I will stick to more of an engineering problem statement. This circuit may also be useful if my science objective can only be reached if I'm pointing at the sun, and I could use this sensor to ensure that the data I collect is validated in the pointing direction. So to break down this problem, how do I know if the sun is in my periphery? Lots of light. What sensor should I pick? Which wavelengths should I focus on? UV, visual, IR? The rest of these slides will solve this. This is a useful diagram I found to help solve our problem statement, as it shows the radiation spectrum that the sun emits. We can use this to determine what wavelength sensor will give us the best chance of seeing the sun. As you can see by the diagram, only 5% of the sun's radiation spectrum is emitted UV. Hence, this may be a sensor that needs large amplification to get accurate readings. On the other hand, 53% is infrared, but the wavelength is spread across a large bandwidth, having around 1700 nanometers of bandwidth to play with. Therefore, we should focus on the next largest area, which is visual light, which makes up 42% in only a 400 nanometer bandwidth. It is also the easiest for us to understand, as we have two visual light photoreceptors on our heads. Just quickly, we can have a look at the crazy amount of sensors that look directly at light. They're split into four main categories that I'll focus on. The first being photovoltaic, which are basically solar panels, and they're used to generate large amounts of energy. These would be applicable as they absorb a large bandwidth of light, and we could track the energy generation to determine the general direction the sun is, but due to this large bandwidth and the FOV, we can find a more applicable sensor. On the other hand, phototransistors let current flow through the legs when light is applied to the sensor. These are great sensors as they can push large amounts of current when there is light, which is good in high power applications. For us, we want more of a passive sensor, the lowest amount of power being used so that we can run our sensor as long as possible. Therefore, we might not want to have a photoresistor as well, as it needs a source of current, such that we can measure the change of resistance based on the light. So therefore, finally we land on the photodiode, which takes in a small bandwidth of wavelengths and produces a small amount of photocurrent based on the irradiance or the amount of light supplied. We can begin to represent our system as a block diagram, remembering that we only represent blocks in which signal flows. So therefore, I don't need anything to show that I'm powering my microcontroller or powering my sensor, as this is assumed. The purpose of the block diagram is to give a high-level overview of what you plan to observe on a specific signal. Your teachers, parents, or friends could look at this diagram and understand generally how your system converts visible light into a number that we can read on our computers. We're going to begin to break down our block diagram into various subsections, starting with the photodiode subsection. We picked this photodiode because we wanted to convert visible light, which wavelengths are shown on the right, into photocurrent. The benefit of this sensor is it generates quite a bit of photocurrent for the lux provided. As you can see by this diagram I'm circling, we have the current generated versus lux. Just take note that this current generated is in microamps. And then the lux is also on a logarithmic scale, which you can see. So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, etc. So you can see that it looks like a straight line, but it's actually not a linear relationship. To further break down our block diagram, we also need to include an amplifier section. As seen in the last slide, we're only generating microamps, and we need to convert that into a voltage that our ADC can read, such that I looked on Google what is the best amplifier for a photodiode, and I found a transimpedance amplifier, which converts and amplifies current into a voltage using a negative feedback loop. And this is seen on the block diagram, and we can talk about it later, why we can include an arrow showing negative feedback, but it's not necessary in all block diagrams. So looking for an operational amplifier, we picked a tried and true LM741 operational amplifier, which is a quarter century old. The reason why we picked this operational amplifier is that it's so old that it has models created around it in all like simulation software, so that if you wanted to simulate our circuit, you get an accurate simulation based on the LM741 operational amplifier. So now, once we've chosen all our blocks, we can put them together into our final block diagram. The block diagram clearly shows the flow of visible light to photocurrent, which is then amplified by the amplifier and converted into an analog voltage, which our microcontroller can read on an analog to digital converter pin. As we need to convert an analog voltage to a value we can see on the screen, we'll use the microcontrollers we already have, which are the Arduinos. This is because they allow us to use an ADC to view the binary value on our serial monitor. I left the connection to the PC off the final block diagram, as in space we won't have our computers connected to our microcontroller, and we'll need something different with the sensor information. For this problem statement, it could turn the sensor into a low power mode if it doesn't see the sun, as in this case we only want our payload to be on when the sun is visible. To build our circuit, we're going to need 6 different things: a breadboard to hold and electrically connect all of our components, jump wires to connect those breadboard nodes together, a resistor kit so that we can choose the correct gain for our signal, the SFH206K photodiode to generate the photocurrent based on the visible light provided, the Arduino micro to convert the analog signal to a digital signal so we can view it on our serial monitor, and lastly, we're going to need a LM741 operational amplifier to convert an amplifier signal. Oh, and also a 9-volt battery to power everything. Our sensor is the SFH206K visible light photodiode. For us to use this sensor properly, we need to understand the graphs given in the datasheet, specifically the photocurrent to lux graph, where we follow the line LP or IP to determine the amount of lux our sensor is exposed to based on the current we read across the terminals. Notice that the grid on the graph isn't even and we step in powers of 10. This means we're on something called a logarithmic graph. I don't expect you guys to know what that means, but we have an exponential relationship. This means it isn't going to be easy to generate a linear relationship. We're going to have to make sacrifices in order to measure the differences in lux magnitudes. This is the pinout for the LM741. I've overlaid the schematic for your convenience. Op-amps are not the most intuitive devices, and I have learnt quite a bit of theory in my undergrad. We don't expect you to know the fundamentals of how they work, but these will most likely be used in all of the analog circuits you build. So all we really want you to do is to be able to Google different configurations of how they can amplify and linearize a sensor. So going back to the last lesson I gave on the Arduino micro, We're going to use that PF7 pin, the same pin we focused on. We're going to need that because it's the ADC, well, it's the first channel of the ADC. You could pick any of those analog pins, but we're just going to go with simplicity, the same one that we went through. So a recap on what an analog pin is. It translates a continuous analog signal into discrete values that our microcontroller can understand and process. Therefore, it will also round down to the nearest bit that corresponds to the continuous voltage value. These pins convert this by utilizing an ADC, or an analog to digital converter. So what are the characteristics of an ADC? ADCs are bounded by two main things: their maximum voltage, normally bound to the supply voltage, which is 5 volts in the case of an Arduino Micro; their resolution, which means the number of bits they have. This number of bits is divided evenly through the maximum voltage, as seen by the diagram shown, where each one of these cross sections is another step in resolution, and then the sensor voltage is measured over time, which at any given time step goes into the ADC and is converted into a binary value based on this 0 to 1024 scale, based on our 10-bit ADC on our Arduino Nano. This is the schematic diagram of our circuit. As you can see, the parts have been represented with their corresponding symbols and labeled with boxes. When you see an integrated circuit or a chip like the LM741 op-amp, you should also label all the pins so that when you build the circuit, it's easy to match the numbers. In this diagram, the photodiode is represented as two components, a diode and a current source, where the current source is the photocurrent. You can click on that orange Volstad link and you can get to that page where the circuit is, and I've set up some sliders so that you can play with the photocurrent and the feedback resistor. See if you can try find the relationship between them. Now that we have an idea of our desired circuit, it's time to size the feedback resistor the best we can. All sensors are not ideal and will not follow the datasheet exactly. Each sensor has a specified tolerance. So if we want to know if our photodiode is pointed at the sun, the best way to get that corresponding photocurrent is to actually take the sensor outside and point it at the sun and record the photocurrent with a multimeter across the pins. Once you have measured this current, we can then head back inside and measure the current inside, or the ambient light, and then we can also maybe measure an intermediate one using our phone flashlight. To find the right feedback resistor using Ohm's law, we rearrange the equation V equals IR to solve for resistance, giving us R is equal to V on I, where V is the maximum analog voltage from the microcontroller, and I is the maximum photocurrent measured when the sensor is in the sunlight. For example, if our microcontroller's maximum voltage is 5 volts and our photocurrent is 1.8 milliamps, we first convert the current into amps by dividing by 1000, giving us 0.0018 amps. Plugging these values into the formula, we get R is equal to 5 on 0.0018, which equals 2777.8 ohms. Since it's impractical to find a resistor with this exact value, we round to the nearest available resistor. However, when rounding, we need to consider whether rounding up or rounding down is better for our needs. Rounding up increases amplification, but might cause our readings to max out too quickly, whereas rounding down sacrifices some sensitivity, but allows us to measure a wider range of light intensities. Therefore, if we're recording light levels over time, rounding down might be the better choice to avoid saturation. Once you have chosen the correct resistor from your kit, it's time to build the circuit as shown. Keep in mind that pin 1 on a chip is usually marked by a notch or small divot. This is important for getting the orientation correct. Also, be sure to connect the battery last to avoid accidentally damaging any of the components. Before powering up, double check with your teacher to ensure that all components are correctly placed. Once confirmed, you can move on to writing and uploading the Arduino code. A helpful tip is to color code all these jumper wires. This is to keep your breadboard organized and much easier to troubleshoot if things don't work as expected. This is the Arduino code I'd like you to start with. We first set up some values and initialize the serial monitor before heading into the infinite loop. In the loop, we record the photodiode's value with an analog read and then print both values to the serial before waiting 50 milliseconds to start again. I'd try changing this code into two threshold values, one being in sunlight, one being in shade, and then having the onboard LED dictate if you're in sunlight or in shade. To begin troubleshooting my circuit, I'd first put my multimeter probes, the black one on ground, the red one on A0, and also changing my multimeter into DC voltage reading. If you're getting a reading of 5 volts when you're in the sunlight and a reading of around 0 volts when you're inside, then the system must be working as intended, and I'd say that maybe my Arduino isn't working as expected and try replacing that one first. If that doesn't fix the problem and you're still getting those readings, then maybe I'd try to swap my photodiode to face the other way. If your photodiode is facing the wrong way, you're actually measuring the dark current, which I won't get into now, but it's not the current we're trying to measure. Then also check to make sure that your photodiode's lead heading into the op-amp is heading into the inverting terminal, the terminal with the minus side on the schematic. Then also double check that your feedback is coming from the output of your op-amp on pin 6 into the inverting terminal, which is pin 2. Also make sure that pin 3 is connected to ground, which is your non-inverting terminal, and also pin 4 is connected to ground, which is your negative supply voltage. And then lastly, make sure that pin 7 is connected to your positive supply. Once you've got all those connections in, your circuit is as intended, and if it doesn't work, I'd slowly start replacing components. I'd use the multimeter to check to see if my battery has voltage. So if you put the DC voltage across the terminals, you should be measuring 9 volts. If you're measuring way below that, that means your battery has lost a lot of power and it's probably flat. If you're not getting any voltage reading on the output of your op-amp, or if it never changes, your op-amp also may be broken. It may be shorting your positive supply rail to your output, which means that you always get 5 volts, or it might be shorting your negative supply rail to your output, which means you'll always get 0 volts. But if the voltage is changing and fluctuating, it might just mean that you've picked the wrong feedback resistor.
Right, so that is it for this couple of weeks of sessions. Hope you enjoyed it. So next week, week 26, debugging hardware. You touched on it a little bit this session with Will, but we'll talk more about how to debug or troubleshoot the hardware or the physical components on your sample payload and apply that to your own payload prototype. And as always, please send through your progress and questions or troubleshooting requests to binarx@curtin.edu.au so we can support you. Thanks a lot and have a great rest of your day.